Hi, everyone. Welcome to the first part of the course on quantum theory. So this is Focus 7. This is actually the second time I've tried to record these first couple sections. So if I sound bored, I'm not. I'm just redoing the exact same lecture that I did about an hour ago. So quantum theory was developed and finished in 1926. And it's a key to understanding all of chemistry. So as you go through the course, think always in your head, is there something that you've learned in chemistry that doesn't require quantum mechanics? So I can't think of anything. So in the late 1800s, scientists started to see things that couldn't be explained with classical mechanics. So that idea from Newton's classical dynamics that you can know where a particle is, how fast it's going. If you know the forces on it, you know how its position and its speed will change over time. And a lot of the reason was with new equipment, new experiments, they were seeing that that's just not true for small particles. So 3 experiments at this time led to the conclusion that energy is quantized, meaning it comes in discrete packets. So that will be the main idea that we get from quantum mechanics. We'll also see the wave nature that's necessary for that to happen, but that's the bottom line. So before you begin this section, go back and review electromagnetic radiation and its properties, which there's a section on the toolkit 13 on page 237. That way you'll remember, you should have learned all of this in Gen Chem, hopefully by now a physics class, but just reminding yourself of frequency and wavelength, intensity, all the properties that we associate with an electromagnetic field. So the 3 experiments that led to the conclusion that there's something wrong. First one is black body radiation. So if we look at page 239 in the text, there's a nice graph that shows you that if you're thinking classically, so it's this graph in the upper right-hand corner, experimentally, what happens is the density of energy as a function of wavelength has this peak shape. And then as you go to shorter and shorter wavelength, which now you should know reminds you that it's higher and higher energy, that peak goes down. So sun, for example, can be considered a pretty perfect black body, radiates all of the different regions of the spectrum, but it doesn't get higher and higher. You don't have lots of ultraviolet or lots of X-rays, which would be way up here where it's going to 0. So experimentally, we see that you have a relatively large intensity of long wavelengths, low energy, and that there's some peak. And this peak would be characteristic of the temperature that's not graphed on here. But what they saw experimentally was this blue line. So, no, theoretically was this blue line, sorry. So the blue line from theory using classical mechanics would say that the density of energy just goes up and up and up and goes to infinity as you get to these short wavelengths, which have a lot of energy. It's called the ultraviolet catastrophe. We know this isn't true. And in order to fix that problem, what you have to add to your theory is this idea that energy is quantized, that the energy at a certain frequency, and this is Planck's constant, always comes in packets. N can be 0, 1, 2, any number, integer. And so you don't have n as a half or n as a quarter or some other fraction. It's always an integer. And so once you put that into the theory, those 2 graphs that I just showed you would match almost perfectly. So adding this idea that energy is quantized takes the classical theory and allows it to match and predict what experiment would show. Same thing is true for heat capacity. We learned a lot about heat capacity in PChem 1, where we learned that it's a measure of how much heat you have to add in order to change the temperature of something. So at low temperatures, experiment did not match theory. So there was a huge difference. And once again, just like with black body radiation, the one thing that you can do to fix it is to assume that energy comes in packets. So if we assume that N is a 0, 1, 2, 3, but not a half or a quarter, then you can develop a theory that will correctly predict what the heat capacity is. Probably most familiar to chemists is the experiments that were being developed with the equipment at that time to look at how atoms and molecules emitted and absorbed energy. So if we look in your book on page 241, we see what you remember from Chem 107. This picture here where you're looking at, this is iron atoms, and you're looking at what energies are emitted. Classical mechanics should just say that this is just flat, that all frequencies are emitted equally or all wavelengths, but that's not what happens. So what happens is you get these peaks where you have energy emitted and then areas where there's none. So there are discrete, just certain quantities of energy that will be absorbed or emitted from electrons within atoms. So we get this fingerprint for iron. You'd have a similar fingerprint for hydrogen or any other atom with peaks in different locations, which is just saying that small particles can't take on a continuous amount of energy. You can't kick an electron a little bit or a lot. It comes in discrete packets. So there are certain energies that you can transfer to electrons, but nothing in between. We look at molecules, it's very, very similar, except with molecules, you have lots of other places. So this upper left-hand graph, you have lots of places you can put energy. So you can put energy into the electrons. You can put energy into the molecule rotating. You can put energy into the molecule vibrating. And when you do that, you put in, just like with the atoms, discrete amounts. Each of these individual peaks shows you that when you look at the infrared spectrum of this molecule, energy to excite the vibrations come in certain sizes, and energy to excite the rotations come in discrete sizes. So same exact idea that we had with atoms happens to molecules. So energy of electrons, energy of any kind of motion, it's all quantized. And then you can develop a theory that will explain the experiments that were going on at the time. So the first concept, or the first idea that led to quantum theory, was the idea that maybe a wave can also have particle nature. That's going to lead us to ask the question, can a particle have wave nature? And then to explain the properties of electrons. So the time this was being developed, I think it was 1924. I thought I had the date on here. Sorry. No, that's for de Broglie. Sorry. Somewhere around 1900, a little bit later, they were doing experiments that were called the photoelectric effect. So if we look at this graph on page 243, I can explain what's going on. So what's going on, if you look at this lower left-hand picture, we have the kinetic energy of the electron that leaves the surface and the frequency of the radiation we're hitting it with. So what you're doing is you're taking a metal surface and you're striking it with electromagnetic radiation, and you're seeing whether or not it has enough energy to pull electrons off the surface. And what you see from this is that these are different things, different atoms. So different atoms have different threshold energies. They have a different amount of energy that it's going to take to pull the electron off. So for example, for sodium, you have to get to this particular frequency before any electrons will be emitted. And then if you go above that frequency, so to higher energy photons, the electrons are going to come off the surface and they're going to leave with a higher kinetic energy. So kinetic energy on the y-axis. And so what that is telling you is that each electron absorbs one packet of energy. So if you're below that threshold, you can increase the intensity of the light at the same frequency. But if it hasn't reached that threshold frequency, it won't matter. You won't eject an electron. So Einstein took these experiments and developed the idea out of that, that light, which was thought at the time to be radiation electromagnetic field, so a wave, can also have particle nature, and he called the particles photons. So this is what Einstein actually got his Nobel Prize for, was the photoelectric effect. Even though it seems like special relativity are some of his more complex ideas, this one doesn't seem that complex, but at the time it was really complex because people weren't thinking of particles and waves to be one and the same within the same system. So what that graph is showing you is that if you have a photon of light and it has energy h nu, so if you read about the properties of light I told you to read about, you'll remember that's the energy of a photon. It's going to be equal to how much energy it takes to pull the electron off the surface. So that's the work function, plus the kinetic energy. So depending on how much bigger the energy of this is compared to this, the electron will leave with more or less kinetic energy. So if this is bigger than this, then the electron just doesn't leave the surface. You don't have enough energy to overcome the attraction for the electron to the surface. So if you rearrange that, you can see that the kinetic energy is a function of frequency, and that the slope of that line, so I should have kept this open, the slope of that line is Planck's constant. So it's one of the best ways to measure the value of Planck's constant. If you notice, the slope of each of these lines is the same, and that should be Planck's constant for each of those. So you can use the photoelectric effect experiments to measure the value of Planck's constant. So if we summarize what the experiments concluded, number one is that photoejection, so the ability for light to pull an electron off the surface, can't occur if the energy of the photon is less than the work function, because the photon would lack enough energy to pull it off. So it would hit the surface, would excite the electron, but it wouldn't have enough energy to pull it off. And the kinetic energy of an ejected electron increases in a linear fashion with frequency of the photon. So that's the equation up here. Our kinetic energy graphed against frequency would be linear, and h would be the slope. Number three, when a photon collides with an electron, it gives up all its energy. So an electron should appear as soon as the collisions begin, provided the photons have sufficient energy. So I'm going to take a break here because I actually got here before and the rest of the video was fine. So that'll be in part 2. So have a good day.